In this lesson, we will talk about the volume of cylinders, cones, and spheres. So let's get started. Let's start by looking at a cylinder. So let's define a cylinder. So a cylinder, it's a very specific prism. Because recall in our previous lesson, we said that a prism is created whenever we join two bases that are equivalent. Now, a cylinder is exactly like a prism, but the only difference is that those bases are circles. So if our bases are circles, then our prism becomes a cylinder. And that's the only difference. That in a prism, it can be any type of a shape as our base, but at least for cylinders, our bases must be circles. And again, all of the different characteristics that a prism has, they get carried over with a cylinder. So the segments that are joining the center of the circular bases is what we call the altitude. So the altitude of a prism, the altitude of a cylinder is, if we take a look at the center of the upper base, and if we take a look at the center of the lower base, and if we connect those 2 points, that's how we're going to be finding the height or the altitude of this cylinder. And again, the length of the altitude is what we refer to as the height. And since the bases are circles, then the radius of the bases is what we're going to recall as the radius of the cylinder. So a cylinder, it's a very specific prism. And again, right now we're just going to take a look at right cylinders. There are other type of cylinders, just like there are other type of prisms, and that's what we call oblique cylinders. These are just cylinders that are not straight, but they're actually tilted. And we're going to reserve that discussion for future lessons. Once we start discussing Cavalier's principle, then we're going to start discussing how can we find the volume of oblique cylinders and oblique prisms. So right now for this lesson, we're just going to concentrate on right cylinders. And again, the right cylinder is whenever our height is exactly, our cylinder is exactly in a vertical line. So how do we find the volume of a cylinder? Well, the volume of a cylinder is equal to the area of the base times the height. Because recall that at least for a prism, we said that the volume is equal to the base times the height. But at least for a cylinder, we know that the base is equivalent to a circle. And recall that the area of a circle is pi r squared times the height. So this is how we're actually going to be defining the volume of a cylinder. Pi r squared times h. Because remember that a cylinder, it's a prism. So therefore, it follows the formula for the prism. But since our base, it's a circle, then we can just, instead of calling the area of the base, we can just call it pi r squared, because that's how we find the area of a circle. So now let me just erase this. So our next figure, it's a cone. So what is exactly a cone? Well, a cone has the same characteristics as a pyramid because a cone, it's a pyramid. But the only difference is that for a cone, our base it's a circle. So the same idea. Everything that we discuss about pyramids can get carried over with cones. But in order for us to call it a cone, our base must be of a circle. And that's what we're trying to say here. Like a pyramid, except that the base is a circle instead of a polygon. So for cones, our bases are going to be circles, not just regular polygons, but we still have the same characteristics as we have as pyramids, where we still have this so-called slant height, which is just the height that we do have slanted, or that we do have on the side of this cone. Is the same idea as just having the height of the side of the pyramid. And again, the height is the length that we have from the center of the cone to the point where all sides are intersecting. So that's what we call here the height. Now, We said that for a pyramid, the pyramid it's equivalent to 1/3 times the area of the base times the height. But now for a cylinder, I'm sorry, for a cone, the base it's a circle. So therefore, we can just modify, and instead of writing the area of the base, we can just plug in the actual pi r squared, the actual area of a circle. And that's how we get this formula right here. The volume of a cone is 1/3 pi r squared times h, because we said that the cone follows the idea of a pyramid. But since the area of the base, since the base is a circle, therefore we can just use the area of a circle instead of a b. So that's how we define the volume of a cone. So the last figure that we want to discuss here is the sphere. And a sphere is the set of all points that are given distance from a given point. So what we're trying to say here is that the sphere, it's made out of a lot of points. And one characteristic that all these points have in common is that if I take the distance from that point to the center of the sphere, so if I take a look at this distance, that's going to be the same distance for all points. So this is what we're trying to say here by saying the set of all points that are a given distance, which in this case, our given distance is d. So there are a given distance from a point where, at least in this illustration, our point is, let's call it O, which is the origin of the sphere. Now, we're not going to derive the formula for the volume of the sphere, but I will be attaching a animation if you want to just manipulate it and get a better understanding. Right now in this lesson, we're just going to state the formula for the volume of a sphere. And we're going to say that the volume of a sphere, it's equivalent to 4/3 pi times the cube of the radius. And again, we're not going to spend time deriving this formula, or at least showing an illustration about why this is true. At least for the sphere in this lesson, I'm just going to state the formula. We're going to apply it. But if you want to learn how come this formula is true, I will be attaching an illustration on our classroom. So this is what we wanted to discuss today. So we have, for a cylinder, the volume, it's equivalent to pi r squared h, because a cylinder, it's a prism, so it follows the idea of a prism. The only difference is that the bases are circles. The volume of a cone is 1/3 pi r squared times h, since a cone, it's a pyramid, but only the base is a circle. And the sphere, we're going to define the volume as 4/3 pi r cubed. So let's just do one example for each figure. So let's take a look at a cylinder here, and let's try to find the volume of this cylinder. So let's start by stating the actual formula that we need. So the volume of a cylinder, recall, that is defined as pi r squared h. So let's see if we get all that information. Do we know what the radius of the cylinder is? Well, notice that here, this is the center, and we said that since this is perpendicular, notice that this line is perpendicular. So therefore, this meets the definition of this being the center of the bottom base. So therefore, here I can see that my radius is 5. So we got the radius. Do we have information for the height? Well, notice that this line is perpendicular. So therefore, we can use this as being the height. So once we have that, it's just a matter of plugging in. So pi, for r, I have 5. For h, I got 4. So now this just becomes pi times 25 times 4. So this is equivalent to 100 pi. But now notice that we're talking about volumes, and the sides were given to us in centimeters. So therefore, our units are centimeter cubes. And again, notice that I left it here as a pi, but remember that at least if we want to compute it, pi, it's approximately 3.14. So if you want a numerical representation of this, all we gotta do is just, so this is an exact representation of the volume, but if we want an approximation, then we can just multiply 100 times 3.14 centimeter cubes. And if we do that, this is going to be equivalent to 314.2 centimeter cubes. So it doesn't really matter the way that you want to represent your volume, if it's in decimal representation or exact, but it's more preferable for you to just leave it as exact, because it's preferable to have exact values than an approximation. But either or is going to be okay. So that takes care of us of our example for the cylinder. Now let's take a look at example of the cone, where recall that the volume of the cone is going to be 1/3 times the area of the base. What the base is a circle, so that's pi r squared times IH. So let's see if we have the information that is needed. Do we know the radius of the circle? Well, again, notice that the line that connects the upper point with the center, it's a vertical line, and more importantly, it's a perpendicular line to the base. So therefore, we can call this the radius of our circle, which in this case, the radius can be seen as 3. And do we know the value of the height? Well, notice that this line right here is perpendicular, so therefore we can use 6 to represent the height. So now that we know the radius, now that we know the height, then therefore the volume is going to be 1/3 times pi r, which we already know that is 3, square, times the height, which is going to be 6. So let's see if we can simplify this. So now this becomes 1/3 pi, 3 to the second, that's 9 times 6. So b is 1/3 pi 9 times 6. That will be 54. And I notice that everything has been multiplied, so we can just write this as 54 pi over 3. And again, let's assume that the size were given to us in centimeters. So therefore, we got centimeters cubed. And again, this is an exact representation of the volume. But again, if you want a numerical representation, we can just let pi be equals to 3.14. So we got 54 times 3.14 over 3 centimeters cubed. And if we do this on our graphing calculator, we're going to get an approximation. And this approximation, it's of about, let me just scroll this a little bit more. And this approximation is going to be about 56.52 centimeters cubed. So regardless, if we represent it as an exact representation of the volume or an approximation, it's fine. And I just noticed that we can still simplify this. So notice that we can go a little bit further, because 54 over 3, that's actually 18. So we can leave it as 18 pi centimeters cubed. So regardless if you want to leave it as an exact number or an approximation, they're both correct, but it's more preferable to just leave it as an exact number. It's preferred for us to have exact values as solutions. So that covers cylinders, that covers cone. Let's just do one example of a sphere. So here notice, it says a plane passes 4 centimeters from the center of the sphere. And again, by a plane, we're talking about just a flat line, or shouldn't call it flat line, but a flat surface. Where in this case, this is the plane that they're referring to, or this is the plane that we are referring to. We're not talking about a physical plane, but we're talking about a geometrical plane, which is just a flat surface. And what we know about this so-called plane, and again, this is just a flat surface, is that it is 4 centimeters. So let me get this. So a plane passes 4 centimeters from the center of the sphere. So here we have the center, and if we measure this distance from the center of the sphere to this plane, that's 4 centimeters. And the radius of this so-called sphere is exactly centimeters, 7 centimeters here. And our objective, notice that the objective that we want to do with all this information is to find the volume of the sphere. So let's recall what the volume of a sphere is. So the volume of a sphere is going to be equivalent to 4 over 3 times pi times r cubed. So with all this information, how exactly can we find the volume of a sphere? Well, recall that one of the definitions here is that the volume, oh, not sorry, here, a sphere, it is defined as a set of all points that are a given distance from a given point, which in this case, notice that the distance from the center to this point of a sphere, it's of 7 units. But if we want to find the radius of the sphere, it should be some kind of a perpendicular line with the 4 right here. But since this distance is 7, and we're saying that a sphere is a recollection of points that are equidistant, so the distance from this point to the center should also be 7. So therefore, we can say that the radius of this sphere is 7. Even though this was just given to us here on the description of the problem, I want for you to understand that the radius of a sphere, at least the r that we're most likely going to be using, is just going to be some kind of a line that must be perpendicular to, I mean, at least when it comes to the relationship between a plane and a sphere. So if we take a look at our plane and we connect the center of the plane to the center of a sphere, but the radius that we're going to be using, it's a line that is perpendicular to the line that connects the center of the sphere with our plane. Or in other words, it's just the distance between the center to any point in our sphere, which again, they're all going to be 7. Because by definition, a sphere, it's a set of points that are equidistant to the center of the sphere. So we can say that the radius is 7. But I wanted for you to see the relationship between a plane inside of a sphere. And that's all we needed, because now we put it all together, then the volume of the sphere is 4 over 3 times pi times the radius cube. And now it's just a matter of computing this. This is equivalent to 343. And if we simplify all this, this is equivalent to 72 pi over 3. So how I got 1372, I multiplied 343 times 4, and I still divided by 3. So let's see if we can simplify this. So this is equivalent. So this will be like an exact representation, but notice that here is given to us in centimeters cubed. So we can leave this as an exact approximation. But if we want to have a numerical representation, all we gotta do is get 1372 multiplied by 3.14. And now that number, let's divide it by 3. So now that's going to be approximately 1436.02 centimeters cubed. So now with this concludes our lesson for the volume of cylinders, cones, and spheres.